Okay. Good evening, everyone. I am Shivani Dhok, and I welcome you all for the week 9 tutorial for the course of Digital Signal Processing and its applications. So, like every week, this week's tutorial will also be divided in two parts. First part will be recap of week 9 content, followed by the questions related to week 9 content. So in this week, we first started with bandstop filter analog transform. So this said that for analog transform for bandstop filter, for frequency transform, we will use this thing. This formula. Similarly, SL, that is in the low pass filter, will replace this by this thing here. Okay. So this thing is analog transform for bandstop filter. After that, we went on to design a FIR filter, that is finite impulse response filter. So basically, we looked at the designing of 2n plus 1 length filter, and this 2n plus 1 length filter, when we are having, what we try to do is we try to make use of the formula of ideal filter, which is H ideal, which is equal to sine of omega c n upon pi n when n not equal to 0. It is equal to omega c by pi when n equal to 0. And we tried to take the most significant values of this filter from symmetrically from left and right side of 0, so as to save our linear phase thing. Okay, so that we did by considering a rectangular window which we wrote as like this. So this rectangular window is 1 for minus n less than or equal to n less than or equal to capital N, and 0 otherwise. And our FIR filter, which is HFIR of n, is simply multiplication of this thing and this thing. So this introduces side lobe and other stuff which we had discussed well in lecture. So this was all that was, this was the broad concepts that were introduced in this particular week. If you have any questions, just let me know. Otherwise, I'll go on with the questions that I had planned to cover today. Okay. So let's start with the very first question. The first question says that we are given with an inductor with inductance L equal to 0.1 Henry and a capacitance with capacitance 0.01 Farad. And these are connected in parallel. So we need to write the Laplace domain impedance in this given form, and we need to find the value of A plus B. So this was a question from last year's assignment. So let's go ahead. So this H of S, okay, let me draw the circuit diagram first. So we have an inductor and a capacitor connected in parallel. So this H of S will be given by 1 upon Ls plus Cs, which is equal to Ls upon 1 plus LCS square. This comes out to be, so if I divide numerator and denominator by LC, then I'll have 1 by Cs upon S square plus 1 by LC. So if I compare these two equations, like this equation which is given to us, this one and this one, to obtain the form of A and S. So this A here is basically 1 by C, and this B is 1 by LC. So by observation, A is equal to 1 by C and B is equal to 1 by LC. Okay, so therefore A, which was 1 by C, and we know that C is given as, C is 0.01 farad. So this is 1 upon 0.01, which comes out to be 100. And similarly, B is 1 by LC, which is 1 upon, this L is given as 0.1. So this is 0.1 into 0.01, which is 1 upon 0.001, which is equal to 1000. So therefore, A plus B is 100 plus 1000, which comes out to be 1100. So this is your final answer. Any questions? This is a simple question. If you have any queries, please let me know.
No queries, madam.
Okay, thanks. Okay, yeah. So let's move on to the second question. So the second question says that for a rectangular window function, which is V of n, of length 2n plus 1 and centered at n equal to 0, what is the value of V of omega for omega not equal to 0? So I'm repeating this question, like this derivation was done in lecture, in class. This was a part of your last year's assignment, but still I would like to repeat this question so that you get a practice of how to go ahead with these kind of questions. So let's start with again writing this V of n. So this V of n, which was my rectangular window function, is equal to 1 for minus n less than or equal to n less than or equal to capital N, and 0 otherwise. So for n not equal to 0, so for omega not equal to 0, we have V of omega as summation n running from minus n to n, like small n running from minus capital N to n, V of n, which is 1, into e power minus j omega small n. Okay, so therefore, let me write it in this page only. Yeah, we're having this thing here. So this I can write as e power j omega n plus e power j omega n minus 1, and so on till e power minus j omega n minus 1 plus e power j omega n minus j omega n. Okay, so this thing here, this series, whatever we are getting, this is a geometric progression with first term as e power j omega n, and common ratio as e power minus j omega. So therefore, v of omega is equal to first term, which is e power j omega n, multiplied by 1 minus e power minus j omega to the power, how many number of terms we have? 2n plus 1, divided by 1 minus e power minus j omega. Okay, so now I can write this as e power j omega n multiplied by e power minus j omega by 2 into 2n plus 1. So basically now I am taking common e power minus j 2n plus 1 by 2. E power minus j omega 2n plus 1 by 2. So this gets multiplied with, so let me take some more space here. So what I have is e power j omega n multiplied by e power minus j omega by 2 into 2n plus 1 multiplied by e power j omega by 2 into 2n plus 1 minus e power minus j omega by 2 into 2n plus 1 whole divided by, I can take out e power minus j omega by 2 outside. Then I have e power j omega by 2 minus e power minus j omega by 2. Okay, now let us focus on this term, and this term. So what I can do is I can write this as e power j omega and take common all these terms which are here. Okay, so I have taken out omega common, so this, then we are left with n here. Here we are having this term, so this I can write as plus 2n plus 1 by 2, sorry, not plus, minus, and 1 by 2 from this part, so plus 1 by 2 multiplied by 2j into e power j omega by 2 into 2n plus 1 minus e power minus j omega by 2 into 2n plus 1 divided by 2j whole divided by 2j into e power j omega by 2 minus e power minus j omega by 2 divided by 2j. So this term just goes to 0. This term goes to 0. This term here is sine omega by 2 into 2n plus 1, and this term here is simply sine of omega by 2. And again this 2j in the numerator cancels out with 2j in the denominator. So we are left with sine of omega by 2 into 2n plus 1 divided by sine of omega by 2. So this thing v of omega is when my omega is not equal to 0. I hope there are no queries in this particular question. If you have any queries, just let me know. Okay. Okay, so let me just move on to the third question. So this is now the same question, but now I need to evaluate it for omega equal to 0. So again, it says that we have a rectangular function v of n used in design of FIR low pass filter of length 2n plus 1 centered at n equal to 0. What is the value of its GTFT at omega equal to 0? That is v of 0. Something random. So yeah. So this is the question that we are having. So now we'll try to solve this using two ways. One will use this above equation and use limits, and one is simple thing that we can do is directly use the formula of DTFT and evaluate it at omega equal to 0. So we know that this v of omega is summation small n running from minus capital N to capital N 1 into e power minus j omega n. So therefore v of 0 will be equal to summation n running from minus n to n 1 into e power minus j 0 n. So this thing here is equal to 1, and we are adding this 1 for 2n plus 1 times. So this comes out to be 2n plus 1. So this is a simple approach. Another complicated approach could be use of limits. So I'll again show that just for the sake of completeness. Of course, you can always go with this method. You don't need to go for limits. Still, let's do it. So we had found out v of omega as sine of omega by 2 into n plus 1 upon sine of omega by 2. So what we can do is this v of 0 we can write as limit omega tends to 0 sine of omega by 2 into n plus 1 upon sine of omega by 2. Okay, then what I can do is I can multiply and divide by numerator by omega by 2 into n plus 1. So I can write this as limit omega tends to 0 sine of omega by 2 into n plus 1 upon omega by 2 into n plus 2n plus 1 2n plus 1 2n plus 1 2n plus 1 into omega by 2 into 2n plus 1 divided by sine of omega by 2, and I can multiply and divide by omega by 2 here. So now these things get cancelled. This 2n plus 1 is a constant, so I can take it outside the limit. Just a second. Yeah, so this I can write as 2n plus 1 into limit omega tends to 0 sine of omega by 2 into 2n plus 1 upon omega by 2 into 2n plus 1 divided by limit omega tends to 0 sine of omega by 2 upon omega by 2. So this numerator thing so this is equal to 1, and this denominator thing is also equal to 1. So what we are left with is v of omega is 2n plus 1. So this is just a complicated approach, but still I wanted to show this. You can very well just stop at this point and this is the simplest approach that we can go with. This is fine. Still I showed that approach. If you have any queries, just let me know. Okay. Okay, if there are no questions, then let me move on to the next question. So this question asks us that how many zeros does V of omega, the windowing function in the frequency domain determined in the previous question, have when the ideal response of the LPF in its time independent form is truncated between minus n to n. Okay, so now if we are looking at our ideal thing, so what we are having is this window function is V of omega, which is again the rectangular function, and we saw that this V of omega is equal to sine of omega by 2 into 2n plus 1 upon sine of omega by 2. So this thing we know. And another thing that we know is this omega belongs to minus pi to pi. This we know. So let me just take one value here. Yeah, this makes sense. So this we know. And the question says that we need to figure out how many zeros, like how many roots does this particular equation have. Okay, so which simply means that we should set this numerator to be equal to 0. However, we shouldn't take into consideration those values of omega where this sine of omega by 2 also goes to 0. So at those points, both of these will have sorry, at that point both of these will not have a non-zero value. Okay, so now what we will look at is first at the denominator. So the sine of omega by 2 will be equal to 0 if omega by 2 is equal to k pi, right? And this omega should be equal to 2k pi. However, this omega is varying from minus pi to pi, and therefore the only value of k which this can if the only value of k that we can consider is equal to 0, which means that for omega equal to 0, this sine of omega by 2 will be equal to 0, otherwise it won't be equal to 0. Okay, so this thing we know. So now the only issue we will face is when my omega is equal to 0. Now let us set my numerator equal to 0. So the sine of omega by 2 into 2n plus 1 is equal to 0, which means that omega by 2 into 2n plus 1 is equal to some k pi, and this we can write as omega is equal to k pi by 2k pi upon 2n plus 1. Okay, now how many values can this k take? Now we know that this omega belongs to minus pi to pi, right? This omega belongs to minus pi to pi. Now if I set my k as minus n, so if I set if k equal to minus n, then I'll have omega equal to minus 2n pi upon 2n plus 1, and this quantity is well greater than minus pi. Now if I have k equal to minus n minus 1, then my omega will be minus of 2n plus 2 pi upon 2n plus 1, and this quantity is less than minus pi, which means that we can't consider the values less than minus n. Means ignore, for unique range, ignore k less than or equal to minus of n plus 1. Okay. Similarly, if k equal to n, then omega is 2n pi upon 2n plus 1, which is less than pi. And similarly, so basically this is a linear function of k, like omega is a linear function of k, so it's fine like to just check the extremes that we are having, because it will linearly just like join the 2 points. And if my k is equal to n plus 1, then my omega will be equal to 2n plus 2 pi upon 2n plus 1, which will be greater than pi. Okay, so we can't take values of k which are greater than n, which means that ignore k greater than or equal to n plus 1, which means that my k should belong to minus n to n only. Now if my k belongs to minus n to n, so the number of values that this k can take, so number of values k can take is simply the cardinality of this set, which is 2n plus 1. But this set also includes the value k equal to 0. And we saw that at k equal to 0, the denominator goes to 0. And also we had seen that at k equal to 0, we have this v of omega as 2n plus 1, which means that by definition of this function, by whatever derivations we had done, we know that at v of omega is non-zero at, sorry, this is not k. Okay. At omega equal to 0, we know that v of omega is 2n plus 1, and it is a non-zero value. So we know that at omega equal to 0, v of omega is 2n plus 1, which is not equal to 0, which means that k cannot take value as 0, which means that this k can take the values from set minus n plus, sorry, minus n minus 1 and so on, minus 1, 1, 2 and so on till n. And the number of values in this set will be equal to 2n. And this number, so why did at these values of n, what is happening? At these values of n, this numerator goes to 0 in a range of minus pi to pi. And we know that only at omega equal to 0, the denominator goes to 0. Otherwise, the denominator is non-zero at every other places. And it is a sign, so it is a bounded function from minus pi to pi, minus 1 to 1, so it won't go to infinity. So, which simply means that the zeros that are contributed are only by the numerator other than at omega equal to 0, and that is indexed by, those are indexed by this integer k, where this integer k can take values in this particular set, and the number of values that are there in this set are 2n. So therefore, number of zeros in v of omega are 2n. Any questions? Any questions in this part? Okay. Okay, so if there are no questions, then let me just move on to the next question. Yeah. So the next question says that if v of n is guaranteed to be odd, then its DTFT v of omega is guaranteed to be option 1 purely real, option 2 purely imaginary, option 3 even, option 4 odd. So now let us try to figure out what we are having. So what is given to us is v of n is an odd function, which means that v of minus n is equal to minus of v of n. Okay, this is by definition of odd function. So now let us find out. And yeah, one more thing that we'll consider is this. Okay, yeah, let's say this v of n is any function that we are having. Any function that ranges from minus infinity to infinity. Let's not restrict us to a window function. Okay, so then this v of omega will be equal to summation n running from minus infinity to infinity v of n into e power minus j omega n. So this thing I can write as summation n running from minus infinity, or rather I can break it in 3 parts. Yeah, this is fine. To minus 1 v of n into e power minus j omega n plus v of 0 plus summation n running from 1 to infinity v of n into e power minus j omega n. Okay, now what we are having here is, in this first term, in this term we'll just replace this n by minus n. So then we will have this as summation n running from 1 to infinity v of minus n into e power j omega n plus v of 0 plus summation n running from 1 to infinity v of n into e power minus j omega n. So this I can write as summation n running from 1 to infinity. This v of minus n is simply minus of v of n into e power j omega n plus v of n into e power minus j omega n. This thing, yeah, and plus v of 0. So we have v of 0 plus, or rather let's say minus summation n running from 1 to infinity v of n into e power j omega n minus e power minus j omega n. I can simply multiply and divide by 2j. and therefore this term here will be sine of omega n. So I have here v of 0 minus 2j summation n running from 1 to infinity v of n into sine of omega n. Okay, so assumption what we have is this v of n is a real function, and this is what we are having here. So v of n into sine of omega n. So this particular factor here is a real function, which makes this particular factor as imaginary. Now let us figure out what happens with this particular factor here. Now this v of n is an odd function, so we have v of minus n as equal to v of n, minus of v of n. So this thing satisfies for all the values of n, which means that this should get satisfied for n equal to 0. So at n equal to 0, we have v of minus 0 is equal to minus of v of 0, which means that v of 0 is equal to minus of v of 0. And when will this be true? So this simply means that 2 times v of 0 equal to 0, which means that v of 0 itself should be equal to 0, which means simply means that this term goes to 0. So therefore, what we are left with is v of omega is equal to minus 2j summation n running from 1 to infinity v of n into sine of omega n, and we observe that this part is imaginary, which means that if v of n is odd, then v of omega is purely imaginary. So this is our answer. Is this clear? Any questions in this particular part? So if we are given a window function, then instead of from minus infinity to infinity, this thing will get replaced by n. So let me just write this also. Any questions? Okay. So now let us go on for a filter designing question for bandstop filter. So this is a common data for all the remaining questions. So our aim is to construct a Butterworth bandstop filter. So here we have FP1 as 1 kilohertz, FP2 as 9 kilohertz. So these are two passband. Right. I think I made some mistake. Yeah, this should be 10. And this should be 6. Yeah, extremely sorry. Yeah, no, 1 second. This should be 9, and this should be 6. Yeah, this is fine now. Yeah. So what we are given is we have this frequency axis, this is 0. Then first thing we'll have is our FP1, then we'll have FS1, then we'll have FS2, and then we'll have FP2. So this we are given as 1 kilohertz, FP2 is 9 kilohertz, FS1 is 4 kilohertz, and FS2 is 6 kilohertz. So let me just write it properly. So this we have, and how will this filter look? So if we are having this thing here, then we will have a pass band edge like this. We'll have some tolerance as 0.15. Then we will have stop band edge, and again we'll have pass band edge. Yeah. So this is the band stop filter that we need to design. We need to design the digital band pass filter. Band stop filter for these given specifications. So like last time's lecture where we designed band pass filter, we'll now design a band stop filter. So specifically I took band pass and band stop because these are the difficult ones to design compared to the normal filters. Okay, fine. So let's start with this sixth question today. So first step, as we had seen last time, was we need to find normalized frequencies. Then we need to find so first we need to find the normalized frequency. Then we need to find the frequencies for the equivalent band pass filter in analog domain and low pass filter in analog domain. So let's start with this. And yeah, one more thing that is given to us is the sampling frequency is 20 kilohertz. Okay, so let's start with this thing. So let's start with step 1, which is finding normalized frequencies. So we have FP1 as 1 kilohertz, and we have sampling frequency as 20 kilohertz. So this means that omega P1, that is small omega P1 for digital filter, this is 2 pi FP1 by F sampling, which is 2 pi into 1 kilohertz divided by 20 kilohertz. So this comes out to be 0.1 pi. Similarly, we have FS1, which was 4 kilohertz, which means that omega S1 is 2 pi FS1 upon F sampling. Yeah. And this comes out to be 2 pi into 4 kilohertz divided by 20 kilohertz, and this comes out to be 0.4 pi. Then we have FS2. So this FS2 is given as 6 kilohertz, which means omega S2 will be 2 pi FS2 upon F sampling, which is 2 pi into 6 kilohertz upon 20 kilohertz. and this comes out to be 0.6 pi. And finally, we have the second passband edge, which is FP2, which is 9 kilohertz, which means that omega p2 is equal to 2 pi fp2 upon f sampling, which comes out to be 2 pi into 9 kilohertz divided by 20 kilohertz, and this comes out to be 0.9 pi. Okay, so now what do we have? We have omega p1 as 0.1 pi, omega s1 as 0.4 pi, omega p2 as 0.9 pi, and omega s2 as 0.6 pi. So this we have the the passband and stop band edges for the digital band stop filter. Then now next step that we need to do is find analog equivalent frequencies using bilinear transform. Okay. So now what we need to do is we need to figure out omega, which is equal to tan of omega by 2. Again, we will be having 4 values for this. So first thing that we had was omega p1, and this came out to be 0.1 pi. So corresponding to this, we will have capital omega p1, which is equal to tan of small omega p1 upon 2, which is tan of, so this thing here is tan of 0.1 pi by 2. So keeping your calculators in radian mode, this comes out to be equal to 0.1584. Next thing that we can find out is omega s1. So this omega s1 is equal to 0.4 pi, which means that capital omega s1 is tan of small omega s1 upon 2, which is equal to tan of 0.4 pi by 2, and this comes out to be equal to 0.7265. Then we have omega s2, which was equal to 0.6 pi, which means that capital omega s2 is equal to tan of omega s2, small omega s2 upon 2, which is equal to tan of 0.6 pi by 2, and this comes out to be equal to 1.3764. And finally, we can find out omega p2, which is analog frequency corresponding to omega p2, and this omega p2 is equal to 0.9 pi, which means that capital omega p2 is equal to tan of omega p2 upon 2. This is equal to tan of 0.9 pi by 2, and this comes out to be equal to 6.3138. So if we summarize, we now have 4 values. So first one is omega p1, which came out to be 0.1584. Then we have omega s1, which came out to be 0.7265. Then we have omega S2, which came out to be 1.3764, and omega P2, which came out to be 6.3138. And these frequencies here are analog equivalent frequencies for band stop filter. Okay, so this completes the second part of this particular question, and now we are left with the third part. That is, we want to construct first a low pass filter, and for that construction we need to figure out what are the pass band and stop band edges for this particular filter, for the low pass equivalent or transformed filter. So this is now our step 3. So step 3, finding omega LP and omega Ls. So we have analog frequency transform for band stop filter as omega L to be replaced as, or rather omega L is equal to B omega upon omega naught square minus omega S1, minus omega. Okay, so for this we need two values, that is B and omega naught square or omega naught. So this B, like we use the same things for that we used for band stop filter. So this B is omega P2 minus omega P1. So this is equal to 6.3138 minus 0.
Madam,
Yes,
I think that is omega naught square minus omega
omega
square.
square. Yeah, sorry. Thanks. Minus 0.1584. So this comes out to be 6.1554. And then we have omega naught square, which is geometric mean of these two quantities, and this comes out to be equal to yeah, this comes out to be equal to 6.3138 multiplied by 0.1584, and this is equal to 1.0001. Okay, so this is what we are having here. Yeah, so now we know this. So now our analog transform becomes, frequency transform becomes omega L is equal to B, we had found out as 6.1554 into omega upon omega naught square is 1.0001 minus omega square. Okay, so now this denominator, this thing is quite close to 1, so we can anyway approximate it to be equal to 1 also. So what we can do is we can just set this as approximately equal to 1. It's fine. So this I can just write as 1 minus omega square. Yeah, so we have this thing here, 1 minus omega square. So now let us figure out what we have for omega P and omega S. So for one thing that we had done was this omega LP, we map it to 1, and this omega LS, we find minimum of magnitude of omega LS1 and omega LS2. Okay, yeah, this we figure out. Now let us find out what is omega LS1. So this omega LS1 will be 6.1554 into omega S1 upon 1 minus omega S1 square. This comes out to be equal to 6.1554 into 0.7265 divided by 1 minus 0.7265 square, and this comes out to be equal to 9.4661. Okay, and similarly we have omega LS2, which is 6.1554 into omega LS2, sorry, omega S2 upon 1 minus omega S2 square, and this comes out to be equal to 6.1554 multiplied by, so this omega omega S2 is 1.3764 divided by 1 minus 1.3764 square, and this comes out to be equal to minus 9.4740. So therefore omega LS is minimum of magnitude of 9.4661 and magnitude of minus 9.4740, which means that omega LS is 9.4661. So now what we have is, we have omega LP to be set as 1 and omega LS is equal to 9.4661. So now we know these three things. Any questions in this part? Any doubts in this part? Okay. If there are no doubts, then let me move on to the next question. So next question says that we need to find out the order and the range of the cutoff frequency. Okay. Yeah. So these two things we need to figure out. So we need to find the order and we need to find out the cutoff frequency range. Yeah. Okay. So let's start with step 4, which is finding order. I think it is step 4. Yeah. Find order n. Okay. So now for Butterworth filter, the formula for order is n should be at least equal to CL of half log of d2 by d1 upon log of omega ls by omega lp. Now this d2 is or rather let's start with d1. This d1 is equal to 1 upon 1 minus delta 1 whole square minus 1. Now this delta 1 we had given as 0.15, so this is 1 minus 0.15 square minus 1, and this thing comes out to be 0.3841, and we have this d2 as 1 upon delta 2 square minus 1, which comes out to be 1 upon 0.15 square minus 1, and this thing here comes out to be 43.4444. So this we know, this we had found out in the last tutorial as well. So now we have the values of our d2 and d1, and we had figured out what is omega ls and omega lp in the previous question. So now let us find out the value of order. So therefore n should be greater than or equal to ceiling of half into log of d2 is 43.4444 divided by 0.3841 upon log of omega ls we had found out as 9.4661 divided by omega lp as 1. So now this thing, if we simplify this, we get as 1.0518, and ceil of this thing is equal to 2. So therefore my order should be at least equal to 2. So let's go with the smallest possible order. So my n is equal to 2. Okay, so now this is my order. And once we have this order, what we can do is we can find out the range of my cutoff frequency. So let's do the step 5. Find range of cutoff frequency. Okay, so we know how to find this out. So we have omega lp upon d1 to the power 1 by 2n less than or equal to omega c less than or equal to omega ls upon d2 to the power 1 by 2n. So now this omega lp is 1 upon d1 we had found out as 0.3841 to the power 1 by 2n. N is equal to 2, so 2n will be equal to 4, so 1 by 4 less than or equal to omega c less than or equal to omega ls. This omega ls we had found out as 9.4661 divided by this d2 d2 is equal to 43.4444, and this is to the power 4. Okay, so this we have, and if we solve these things, so we get something like this. We have 1.2702 less than or equal to omega c less than or equal to 3.6871. So this thing here is the allowed range of cutoff frequency. Any questions? Okay. Okay, if there are no questions, then let me move on to the next question. So now the next question says that construct the analog low pass filter by considering omega c as the midpoint of the allowable range of the cutoff frequency. Okay, so what it says is we need to set omega c as the midpoint of these two, so that we can construct by taking average of these two things. So this is simply equal to 1.2702 plus 3.6871 divided by 2, and this comes out to be equal to 2.47865. So this is now my omega c, and using this omega c, just a minute. Yeah, so using this omega c, now we need to construct our h analog of s. Now we know that this h, we have two order is 2, so we have two poles. So this h of s, or let's say h analog of s but low pass, will be equal to omega c, or yeah, omega c square divided by, this has to be divided by s minus s0 into s minus s1, where this sk's are equal to omega c into e power j 2k plus 1 plus n upon 2n into pi, which for our values of n comes out to be e power j 2k plus 1 plus 2, that is 3, upon 2 into 2, that is 4 pi. So s of 0 comes out to be omega c into e power j 3 pi by 4, which okay, and s of 1 comes out to be omega c into e power j 5 pi by 4. Okay, so now let us substitute that in whatever we are having. So this h analog of s lp is omega c square divided by s minus omega c into e power j 3 pi by 4 pi, sorry, 3 pi by 4 into s minus omega c into e power j 5 pi by 4. Yeah, so now let us try to simplify this. So we have omega c square upon s square minus omega c s into e power j 3 pi by 4 plus e power j 5 pi by 4 plus omega c square into e power j 8 pi by 4. So this thing here is equal to e power j 2 pi, and even integer multiple of pi, even integer multiple of pi, which is actually raised to e power into j. So this thing here comes out to be equal to 1, and this thing here is equal to, so this e power j 3 pi by 4 is actually equal to minus 1 by root 2 plus j times 1 by root 2 plus minus 1 by root 2 minus j times 1 by root 2. So these things get cancelled and this leads to minus root 2. So 2 minus 2 upon root 2, which is equal to root 2. So therefore H analog of S, which is basically LP, low pass. So this is omega c square upon S square minus, so this will be now plus root 2 into omega cs plus omega c square. Okay, so this we are having. Now let us substitute the value of omega c, which we had found out. So now we have H analog of S low pass filter is equal to omega c was 2.47685 square divided by S square plus root 2 into 2.47685 S plus 2.47685 square. This comes out to be 6.1437 divided by S square plus 3.5053 S plus 6.1437. So now this is the analog low pass filter which we are having. Now the next step that we need to do is, okay, yeah, so this is what we wanted to find out in this particular question. Any question in this part? Any queries in this part? Is it clear? Is it clear? Is it fine? Hello, am I audible? Hello.
Yes, madam, audible.
Okay. Any questions?
No questions, madam.
Okay. Thank you for responding. Okay, if there are no questions, then let me move on to the ninth question. So now the next step is we need to find the bandstop filter by performing the analog transformation. So now we have, this is which step number? This was step 5, this was step 6. Find analog LPF. Now let us go on for step 7. This is finding, or rather analog transformation. To get our band stop filter, and for this particular thing we have replace the S variable for H analog of S by Bs upon omega naught square plus S square, which we had found out as 1 upon 1554 S upon S square plus 1. So we need to replace it by this factor here. So now we have this H analog of SL LP as 6.1437 divided by S square plus 3.5053 S plus 6.1437. So therefore, now H analog of S, which we actually want to find out. So this is SL, this is also SL. So we'll now replace SL by this particular transformation. So we have 6.1437 divided by 6.1554 S upon S square plus 1 square plus 3.5053 into 6.1554 S upon S square plus 1 plus 6.1437. So now this thing here I can write as 6.1437 into S square plus 1 whole square divided by 6 point, so this quantity here is 37.8889 S square plus 21.5765 S into S square plus 1 plus 6.1437 into S square plus 1 square. Now we have 6.1437 S to the power 4 plus 2S square plus 1 upon this is 37.8889 S square plus 21.5765 S cube plus 21.5765 S plus 6.1437 S square plus 12.2874 S square, this is S to the power 4 plus 6.1437 into 1. Yeah, so this we have. Now if we combine, so we have here 6.1437 into S to the power 4 plus 2 S square plus 1 divided by, we have S to the power 4 term as 6.1437 S to the power 4 plus S cube terms are this one. So this we have as 21.5765 S cube plus, now we'll have S square terms which are this one and this one. So this comes out to be equal to 50.1763 s square, plus then we have s terms. So this is that term. So this is 21.5765 plus the remaining term is 6.1437 constant term. Okay, so this we are having. Now let us try to simplify this. So if we observe carefully, we have,
Madam,
yeah,
last but one term, add yes. Yes, yes.
yes, thank you. Yeah. Huh. So now if we observe carefully, this term here, this term here is little bit common. So we can make, yeah, we can simply divide by that term in numerator and denominator. So what we have is s to the power 4 plus 2s square plus 1 whole thing divided by s to the power 4 plus 21.5765 divided by 6.1437 s cube plus 50.1763 upon 6.1437 s square plus 21.5765 upon 6.1437 s plus 1. Okay, and if we simplify this, we have h analog of s, and this comes out to be equal to s to the power 4 plus 2s square plus 1 divided by s to the power 4 plus 3.512 s cube plus 8.1671 s square plus 3.512 s plus 1. So this thing here, this thing is my analog band pass filter. Sorry, band stop filter. Is this part clear? Any questions in this part? Okay. If there are no questions, then let me move on to the last part of today's tutorial. So now the last step that remains is we need to convert this analog band pass filter, analog band stop filter, whatever we had designed, into its discrete time equivalent, and that we'll do through bilinear transform. So the last step, so which was the step 7. So let's do the step 8. So now we'll apply bilinear transform to get h of z, that is discrete time filter. Okay, yeah. So we have this. So what does bilinear transform say? So we need to replace this S by 1 minus Z inverse upon 1 plus Z inverse. We need to do this. That is, this H of Z is basically equal to H analog of S, but now this has to be evaluated at 1 minus Z inverse upon 1 plus Z inverse. Okay, so let me just reiterate this H analog of S here. So this thing was equal to S to the power 4 plus 2S square plus 1 divided by S to the power 4 plus 3.512 S cube plus 8.1671 S square plus 3.512 S plus 1. So therefore H of Z will be equal to, so let me just take a little bit downwards. Yeah, so this thing will be equal to 1 minus Z inverse upon, do it in this way, 1 minus Z inverse upon 1 plus Z inverse to the power 4 plus 2 times 1 minus Z inverse upon 1 plus Z inverse square plus 1 divided by 1 minus Z inverse upon 1 plus Z inverse to the power 4 plus 3.512 into 1 minus Z inverse upon 1 plus Z inverse to the power 3 plus 8.1671 multiplied by 1 minus Z inverse upon 1 plus Z inverse square plus 3.512 multiplied by 1 minus Z inverse upon 1 plus Z inverse plus 1. So this is what we are having here. Let us try to simplify it a little bit. We won't simplify it to its final answer. So therefore this H of Z is equal to, so if we look at the numerator, we can write this as 1 minus Z inverse to the power 4, 1 minus Z inverse to the power 4 plus 2 times 1 minus Z inverse square into 1 plus Z inverse square plus 1 plus Z inverse to the power 4 whole divided by 1 plus Z inverse to the power 4. And in similar way, this denominator we can write as 1 minus Z inverse to the power 4 plus 3.512 into 1 minus Z inverse cube into 1 plus Z inverse plus 8.1671 into 1 minus Z inverse square into 1 plus Z inverse square plus 3.512 into 1 minus Z inverse multiplied by 1 plus Z inverse to the power 3 plus 1 plus Z inverse to the power 4 And again, this whole thing is divided by 1 plus z inverse to the power 4. So these things get cancelled. And finally, we have, therefore, h of z is equal to, we have 1 minus z inverse to the power 4 plus 2 times 1 minus z inverse square into 1 plus z inverse square plus 1 plus z inverse to the power 4 divided by 1 minus z inverse to the power 4 plus 3.512 into 1 minus z inverse cube into 1 plus z inverse plus 8.1671 into 1 minus z inverse square into 1 plus z inverse square plus 3.512 into 1 minus z inverse into 1 plus z inverse cube plus 1 plus z inverse to the power 4. So this thing, if we go on simplifying further, we can bring it in the form of polynomial in z inverse upon polynomial in z inverse, but it will take a lot of time, so let's keep it in this concise form. So this thing here is now our discrete time or let's say digital filter or digital band stop filter, which we designed using Butterworth approach or Butterworth method. Any questions in this part? So now one thing that I would like you to notice is here the highest power of z inverse or z in both numerator and denominator is 4. So this Butterworth band stop filter is an order 4 filter. However, the low pass filter which we derived now, that was order 2. But now this transformation, this analog transformation which we did here, this is a second order transformation. This is a second order transformation. We are having s to the power 2 here. So now this thing is leading to doubling of the order of the filter which we are having. So if I get n equal to 2, which means that my band stop filter at the end, whichever I'll get, that will be of order 2n. So if my n is equal to 2, it will be n equal to, like order of the final filter will be double of 2, that is 4. However, when we are designing a this whatever statement I made is true for band stop and band pass filter both, because in both the cases we are having a second order transformation. However, when we are having our high pass filter, it's simply omega p by s. So it is still a one order or a order 1 transformation. So there won't be any change in the order of the filter. However, here we'll have 2 times the order of the filter or the low pass filter which we had designed. So let me just again go through whatever we did in this last part of the question, just a quick recap. So our aim was to construct a Butterworth bandstop filter. So basically we wanted to construct a digital filter with specifications given to us in this fashion. So we had passband edge as 1 kilohertz and 9 kilohertz. We had stop band edges as 4 and 6 kilohertz. Then we have sampling frequency as 20 kilohertz and the passband and stop band tolerances are given as 0.15. So based on this, we need to construct our filter. So the first step was to find the normalized frequency, and this normalized frequency can be found out using the formula as omega equal to 2 pi f by sampling frequency. So since we had four different frequencies, that is FP1, FS1, FS2 and FP2, we will get corresponding frequencies, which was small omega p1, omega s1, omega s2 and omega p2. And these four sets are basically the frequencies, or rather passband and stopband edges, for the bandpass filter or equivalent bandpass filter in digital domain or discrete time domain. Okay, I mean for discrete time filter, these are the passband and stopband edges. Now once we have this, we need to pre-warp them using the bilinear transform to get the equivalent analog frequencies, and that is done by doing this bilinear transformation, which is omega equal to tan of small omega by 2. So again we had these four values, and for these four values we have this omega p1. It will give me capital omega p1 using this formula tan of omega p1 by 2. And in similar fashion, we will have capital omega p1, capital omega s1, capital omega s2 and capital omega p2, and these are analog, these are the passband and stopband edges for the equivalent bandstop filter, which is analog. After that, in order to design further, we'll do frequency transform, analog frequency transform, because we are going to first design a low pass filter and then transform it to a bandstop filter. So now in order to find omega LP and omega LS, we'll apply analog frequency transform for bandstop filter, which is given by this formula. And in that we have this term B and we have this omega naught square. So we'll figure it out using these equations, and then we'll do this thing. And this omega ls, which has to be a single quantity, so we'll apply the stringent uh, constraint by setting it as minimum of magnitude of omega ls1 and omega ls2. Okay. So now we have omega ls1 and omega ls2, and then we'll select omega ls as minimum of these two quantities, which comes out to be 9.4661, and we have set omega lp as 1. So we have these things. And once we have omega LP and omega LS, now we are free to design our low pass filter. And in order to design this low pass filter, we require two things: order and cutoff frequency. So in order to find order, the formula is like this, and for that we need this D2 and D1. This D2 and D1 is obtained by these two formulas here, and using these two formulae, we obtain D2 D1 and substitute it in this formula. We know the value of omega ls, which we had, and omega lp, which we had found out in previous question or previous step. So after substituting all the values for omega ls, omega lp, delta d1 and d2, we have this thing. So this order has to be at least equal to ceil of this function, which is 2. So we consider the least possible order, which is n equal to 2. So once we have this n equal to 2, using this we can find the range of the cutoff frequency. So range of cutoff frequency is given by this formula. We can substitute the values and find the allowable range of cutoff frequency. Now in the next step, we were asked to construct the analog low pass filter for some cutoff frequency, and the cutoff frequency was asked us to take the average of the high and lower end edge of the allowable frequency range. So that came out to be something like this. And since the order was 2, that is n equal to 2, so we have two zeros for this particular filter. So this h analog lp of s is omega c square upon s minus s0 into s minus s1, and this sk is given by omega c into e power j 2k plus 1 plus n upon 2n plus 2n into pi. And if we simplify this and figure out the values of sk's, and then we can just substitute them in this transfer function. So if we simplify, we will get a transfer function which came out to be something like this, and this is the transfer function for analog low pass filter. Once we have the transfer function of this analog low pass filter, the next step is to find out the transfer function for the band stop filter, and for that we need to perform analog transformation, and this analog transformation is given by this formula here. And so basically we need to replace this SL, which is the variable or independent variable for analog the transfer function of analog low pass filter. So we'll replace this SL by this particular value everywhere. So once we have done that, and after simplifying, we'll get another transfer function which is H analog of S, which comes out to be something like this. And this thing here is basically the transfer function for analog bandstop filter. So now we at least have a bandstop filter. The only step that remains is to use bilinear transform and get the discrete time filter or the digital filter. And in order to do that, we will use bilinear transform. So we'll get H of Z by setting S equal to 1 minus Z inverse upon 1 plus Z inverse in H analog of S. So after we do that, and after some simplifications, we get a transfer function which can be further simplified in the form of polynomial in Z upon polynomial in Z, or polynomial in Z inverse upon polynomial in Z inverse. And if we do that, we'll have the transfer function or Z transform of or system function for this particular discrete time bandstop filter for Butterworth filter. So this is the entire process of constructing a bandstop filter from the given specifications. If you have any questions, please let me know. This was the last thing that I had time to cover today. If you have any questions, please ask. Otherwise, you are free to leave the meeting. Thank you for attending today's session.